All right, guys, good morning. Let's get started. Thank you all for coming. Should be a good, interesting conversation to have this morning, a lot to talk about. So let's get started. So we're going to be talking about some of the work that we have been doing at Pluralsight, developing a real-time / streaming data platform, kind of putting together a lot of different technologies behind the scenes to make that happen. And before we get started, let me just give you guys a little bit of a background of who I am. So my official title is Data Platform Architect at Pluralsight. Before Pluralsight, I spent a few years at Rackspace, kind of doing the same thing, working with their data platform team. And before that, Walt Disney World, that's what it stands for, back in Orlando, Florida. And if you don't know about Pluralsight, Pluralsight is an online learning technology platform. It is subscription-based in the sense that you pay a flat fee per month, and you have access to a bunch of technical courses from gaming development to data, fast data type of stuff. And the business model is very, very data-driven. So we're trying to capture a lot of data, real-time data, to drive like recommendations, video service, CDN changes, all these kinds of different things to make the experience of the user, the end user, a lot better. So I started at Pluralsight back in 2015, a little bit over 2 years ago. And when we started, like in the beginning, this is kind of how our data platform looked like. As you can tell from the picture, it's very Hadoop-centric. That's where the elephant's right there in the middle. And it was very tied. It was very tied to the Hadoop ecosystem. So we had things like Python jobs, writing files to HDFS, and most of the data was surfaced by either a combination of Hive and Impala. And it worked well for like maybe 6 months to 1 year, but it got to a point that there was so much data that we were ingesting that, and it wasn't easy to discover the streams and the data that we had in HDFS, that a lot of the data requests that we had to come through the data engineering team. And because of that, the development team and the development time kind of became the bottleneck. Because now we had the entire business, entire organization coming to us, asking for us to write scripts and reports, and that's not the goal of a data platform. So for me, if you think about data platform, we're talking about that, right? I mean, you want to come up with something that really empower your user base. If they want to run ad hoc scripts, if they want to run Spark jobs, if they want to run any type of data discovery, you want to allow them to do that. If it gets to the point that there is a centralized team that they have to talk to do any of that, it's time to kind of take a step back and be like, hey, we're doing something wrong because empowerment is gone. So it's a combination of empowerment and self-service. Those are things that we should strive for as data platform engineers. So we took a step, I mean, we realized that, right? So we took a step back and like, how do we fix that? So what's going on? How can we make that better? And we came up with a very loosely defined set of requirements, functional requirements, if you want to call them like that, of things that we want to accomplish in our data platform. We wanted the data to be discoverable. And that was kind of one of the number one things that we came up with. Because we had so much data in Hadoop, but there was no schema. There was just a bunch of JSON files. And it was very hard for anybody who had no knowledge of that business domain to do anything with that data. It was just too much of a black box, and a lot of it. So it was more like a dirty lake, almost. We wanted it to be like a flexible contract. And I'll explain what that means. But the idea is that we don't want to tie ourselves to a specific data format. We want to do Parquet. We want to do Avro. We want to do just sequence files in Hadoop. That's the idea. And we don't want to tie ourselves to any specific technology. That's one of the key points to drive home as well. And that's what I mean by abstraction. Before, we were very tied to Hadoop. So even changing Hadoop, if you want to change from, even upgrading Hadoop was a little bit of a challenge because it was very tightly coupled. And the idea behind having a new platform was to provide a layer of abstraction on top of these underlying systems. We want it to be adaptable, meaning that grows with the business, right? I mean, when we're capturing more and more data, and we want our infrastructure to be able to grow with that as well. We don't want to have to redo it. And open and extensible in the sense that if you want data science, data engineering, data analytics, they should be able to contribute to this platform as well, and their plugins or extensions or things like that. And the more that we talked about this, the more that we realized that we're actually pretty close to reactive. A lot of the reactive principles, they do fit within that mindset, within the architecture. And I'm going to spend just a few minutes kind of going over them to set the context for the rest of the conversation. So when you talk about reactive principles, there's like 4 major tenets that we look at. Responsiveness, elasticity or elastic, message-driven systems, and resiliency. And they're fundamental changes to your architecture, meaning that it's not something that you can write in 5 lines of code. It's something that you have to think about from the beginning of time, if you want to think about that. And the cool thing about these traits is that there's a lot of intersection between them, even though they are listed separately. If you develop something that's elastic and message-driven, you get both of them. You get resiliency and responsiveness just by default. So they're also language agnostic, right? The idea is just a set of very broad architectural concerns that we can implement in any language. And when we talk about responsiveness, so that's the first one, right? Everything else kind of derives from the application being responsive. It doesn't really matter if you have like the best, like a Kafka, an amazing Kafka Spark cluster, if somebody runs a job and it takes like 10 minutes for the job to run. So responsiveness is like, how does your application or your platform react to load, to increasing loads? Because like any data, same thing for a platform. There are times of peak ingestion. Like for instance, when Pluralsight releases a new course, we ingest a lot of data about that course. So it kind of comes and goes in web. And that's the idea behind responsiveness, is that can you keep that same level of response throughout this entire, throughout these ebbs and flows of traffic? And elasticity is the other one. So elasticity, I mean, we have all probably heard about scalability, right? I mean, that's one of the things that we heard about, that we hear about in software engineering. And scalability is awesome, but the elasticity takes that a couple of steps further. The idea behind elasticity is the ability to scale on demand. Kind of like EMR, Amazon EMR, they do a little bit of that. But we're talking about Reactive is a little bit lower level. We want that to be in our code base as well, not only in our infrastructure, but we want our code construct to support that. And elasticity is also the ability not only to grow, so as you have more traffic, to scale both up and out, but when the traffic kind of slows down a little bit, there's no reason for you to keep running 10 instances of that actor anymore, because it's just more expensive. You just, like compute time and memory time, you want to be able to bring that down. So you can think about a connection pool, like a JDBC connection pool, kind of like that kind of shrinks and grows, but we're talking about more for software constructs at that point. And this is at the very core, right, of any reactive system. If you're working with reactive systems, you're going to come across this a lot, how to make your system elastic. And these are kind of the four things. I mean, if you're hitting those, you're in a good path for elasticity. So asynchronous messages, making sure there's no threads blocking. Everything should just be asynchronous. Share nothing. We value locality as much as we can. We don't want resource constraints. We don't want contention. We don't want anybody sharing anything. As much as we can keep things localized, that's better. We want to approach problems divide and conquer, in the sense that instead of having a massive method or a nectar or a service that does everything, we want to have that very multiple little small tasks that work all asynchronously together through a supervisor that kind of grabs all that information later. So that's the divide and conquer. Small asynchronous tasks working together towards the goal. And location transparency, we'll talk more about that later, but that's also a big component, but we'll get more into. The idea is that you as a client, it shouldn't matter to you where that service is running. It could be running within the same JVM, within the same VM that you are now, or it could be running across a network or a different data center. The idea is that you access that node, that service, the same way. That should be transparent. And the other one that's pretty cool to talk about is resiliency. Resiliency, when you talk to, when you're trying to tie that to reactive terms, is basically how your system reacts in cases of failure. And I like to talk about this because as software engineers, a lot of teams, we try to shy away from failure, or we don't want to deal with it because it's too complex or too complicated. And we're going to talk about that a little bit. But the idea behind resiliency, that it's more than just fault tolerance. It's can you keep the same level of functionality, of responsiveness, while your system is running in a degraded mode. It's not the 400 or the 404 that you may see on a website because the credit card processor behind the scenes is down. It's not that. That's not being resilient. It's how can you keep kind of waiting for the systems to heal themselves and then heal yourself as well. It's kind of like this, right? How long can you keep going? And the idea in a resilient system is that you keep going until the underlying system is back. And we'll talk about that later. When we talk about the actual platform, how we're doing that in our case. And going back to software teams, right? Most teams that I have worked with in the past, we don't really have a disaster recovery plan. And if you translate that into code, and this is Java code, but it kind of looks something like this, along those lines, right? This is maybe a little too much, but the idea is that you have all these potential errors points of errors in the application. And what you're trying to do here, trying to do all these tries and catches and nested tries and catches, that doesn't do anything. That does not make the system resilient. All you just did there is made the code really, really hard to read. It's kind of messy. Things are still going to break. It kind of looks like this, right? I mean, you're trying to catch an error. It's like a moving target. There's no way to catch all the errors in an application. Because if you think about it in reactive terms, we should really look at an error as another state of the application. Just like the application has started, it may be being initialized, or it may be like stopped. Error is just another state. And we should be able to react to that just like we do like with callback methods, pre-start in Akka, post-stop in Akka. There should be one on error. And that you route all your calls through that same method. And then when a thing comes back up, you go back, you unstash those messages, whatever they are, and then keep the processing. And that's the idea is this, right? I mean, keep calm and just let it crash. And usually when you bring that out, like to product managers, they react like this. What? You're going to let the application crash? No, you're crazy. But that's not what we mean, right? I mean, it's not like we're going to let the application crash or the website go down. That's not it. It's just that we are going to develop our systems differently to support that initiative. We're not going to freak out if things crash. We're going to deal with the crash, with the failure, just as we deal with an application being started. It's the same idea. And the reason behind that is because software systems are complex systems, especially today. I mean, nowadays with microservices and reactive a data platform, that you have all these different systems that have to work together. The complexity level is up, I don't know, tenfold at least. And we have to realize that we're dealing with very complex systems. And there's this two quotes from Richard Cook that I like to bring up that basically says that complex systems, they run as broken systems and as degraded systems. So there's no way around that. We have to realize that our software is broken. We shouldn't be able to try to catch all exceptions or errors because you want to get ops genie alerts at like on Saturday morning at 2 a.m., right? Or because that's kind of how most teams deal with errors, like an ops genie or a Slack alert, right? There are better ways to handle with errors. And then just really quick, I get asked this question sometimes too, when we're talking about complex and complicated, the difference between them. I like to refer to software systems as complex. And the difference here is that something that's complicated, you can think about something that has many different working parts. And they kind of all work together in very specific terms. But the major difference is that you can learn that. There may be a lot of training in case of a brain surgery. This is a complicated example, right? Because you can go to school. If anybody in this room want to become a brain surgery, it would be kind of crazy, but we could learn it. It would take us a long time, but we could learn it, right? If we had a little crazy in that. I'm joking. All right, but so the idea is that it's repeatable. There's a set of instructions, a blueprint that you could follow, as opposed to something complex like cell division. There's no way, there's no blueprint. There's just a bunch of individual asynchronous almost tasks kind of running together. And the output of all of those tasks together is the coherent answer. And in this case, there's no blueprint. It doesn't matter if you have a blueprint or not, because each part is just completely independent from each other. And it's their interaction that makes the system coherent. And that's the idea that behind software systems as well, the same thing. We should look at software systems that way, as being complex, a bunch of asynchronous parts moving together. We shouldn't try to control everything, but we should try to control the coherence between those parts that are moving at the same time. And then the last one is just message-driven. And the idea is that we're sending messages back and forth, and the system, the platform, must react to those messages. And you see, these are like the four major principles behind a message-driven system. And you can start to see here there's a theme that's kind of rising, right? I mean, asynchronous again, isolation, we talk about that for elasticity, and location transparency. But one of the things here that we do with message and resiliency is that errors in a reactive system should just be represented as messages. So if there's an error operation somewhere, we wrap that within a message, just like anything else in the system, and we propagate that, either through an event, like an event stream, or to the other actors who are waiting for a response. So the error condition itself just becomes a message. It's a message. And the expectation is that both producers and consumers, in the case of a data platform, will be able to react and handle that error situation, whatever that means for them. And then we go into more detail about that. All right, so now that we know about this, let's talk about Pluralsight and how we're implementing some of these features internally within our data platform. So a lot of our development kind of falls under this umbrella. It's a combination, it's a collection of different projects that we named internally Hydra. And Hydra is we're not trying to rewrite Kafka or Spark or Akka, no way. It's just a tool to integrate and to abstract all these tools together in a way that should make it easier for end users to consume data and to produce data to a centralized log or a centralized platform. They all know, we talk to the engineering teams at Pluralsight, they know we use Kafka and Spark and Kafka Streams and Akka, but the idea is that those are implementation details. We don't expect anybody to talk to Kafka directly. Or if they want to run Spark jobs, that's okay, mostly on the data science side. But for engineering teams, we want to keep that as much behind the curtains, behind the scenes as possible. Because the idea is, I mean, this is a very fast-moving space, right? There's Apache Pulsar now that looks very promising, right? So if you guys haven't looked at it, it's worth just looking through the Apache webpage. That basically fills a lot of the gaps that Kafka has. So that's the idea. We may upgrade to that eventually, right? So yeah, so Kafka serves the purpose right now, but we don't want to be tied to that in the sense that if we upgrade it, everything breaks. No. So that's why and that's what Hydra fits in, is having that API layer around everything. And this is kind of what it looks like in terms of components. We do a very explicit, a very clear boundary between data ingestion and data replication or streaming on the other side. And I put this schema, there's a schema manager, we use Confluent. We leverage some of the Confluent schema registry, and we talk about that. But the idea is that we have these three different major components that are part of Hydra that make up the data platform. And ingestion, we're going to talk about that. And the portal is more of a manager. It's like a metadata manager. If you want to add a new schema, add a new Kafka topic, or if you want to do like authentication, add users, that's where you'd go to do that. It's more of an admin tool. And then on the other side, Hydra Streams over there, we're trying to make, that's newer. And the idea is to make that a stream federation layer. You know, I'll explain what that means later. But the idea is that we want Hydra Streams to sit in front of the different streaming frameworks like Spark Streaming, Kafka Streams, and Akka Streams, and then basically have that piece of the API basically spin up those jobs into those different systems. Look at the job and say, hey, this looks like a Kafka Stream job. Let's just do it as a Kafka Stream job. This is really a Spark Streaming job because it has Spark ML functions in them. So let's spin that up as a Spark ML job. So that's the idea. And so like we talked about, the technologies that we use are primarily Akka, a lot of Akka. All of this is a massive remote actor system. Spark for some of the data replication after the fact that it has been ingested into Kafka. So those are the primary tools that we integrate. And the integration of those tools, that's what we call Hydra, right? There's different components. So let's talk about Akka really quick. Why did we pick Akka as our, it's probably the major implementation detail of the platform is Akka. And if you think about Akka, it's a set of open source libraries that provide a lot of the plumbing, the reactive plumbing behind the scenes. So if you want to do things like highly scalable, highly concurrent, thread-safe applications, Akka is kind of the way to go, because you don't have to worry about any of that. That's given to you like from outside the box, right? I mean, you just get it for free. And then you can basically concentrate on the things that really matter. So you don't have to worry about things like the JVM memory model. You don't have to worry about atomic variables, volatile modifiers in Scala. Akka handles a lot of that. And some of the features that we like about Akka is distributed by default, right? So there's a lot of, it's very easy to deploy actors remotely, deploy actors on an Akka cluster. Your entire application can be configured to both scale up and out by changing configuration files. It's fault tolerant. I mean, actor systems have a different way to error handle. I mean, to handle errors. That's very close to the reactive paradigm that we talked about, the resiliency. There's no exceptions. It's just basic supervisor strategies. And so Akka by itself is a fault tolerant system because it implements that model. And we'll talk about that in a little bit. And completely asynchronous. Akka by default is asynchronous calls, right? And we talk about that, what that means as well. But the idea is that the Akka applications are very responsive for that reason, because it's a bunch of small tasks running asynchronously, and there's communication between those threads. And because of that, it's highly concurrent. Right? I mean, the level of concurrency that you can get with an Akka application is pretty amazing. But there are some challenges as well, and there's a few. These are the ones that I kind of, just to, like the four that came to my mind when I was putting the slides together. Remoting, like location transparency. So Akka implements location transparency with the concept of remoting. And it works, I mean, it works well. The thing is that once you make your actor system remote, now all your messages that are sending back and forth between the actors have to be serialized. And there is really no super cool, amazing serialization library for Akka right now. They discourage you from using Java serialization because that's just not good. I understand that completely. But the alternatives are not that. There's some work to be done there. We use Cryo. Cryo is like from Twitter, and there's a Akka wrapper around it. And it's really fast. It's good because it has a lot of speed, but if you want to get the level of speed that Cryo offers, you have to basically register classes, give classes IDs on all the remote actor systems. They have to match. And you don't really know if there's an error until runtime, because there's not a compile time thing. And the errors are very cryptic. It's like this class header did not match over here on this side, and like, what do I don't know, what do I do? So that part is not fun, not fun at all. It's to the point that we also almost consider just let's not do remoting anymore. Let's just have like the actor systems completely deployed across different nodes as opposed to having only this section deployed, because that's what we're trying to do, trying to slice and dice the actor systems. But I think we got it to a situation, to a state that it's pretty stable. Type safety that comes up as well. But this is not so much about Akka. It's more about like a message-driven system. There's no, I mean, if you're coming from Java or C#, any object-oriented language, programming language, you're used to interfaces, right? I mean, we're used to dependency injection. We're using to a very clear contract. In a message-driven system, you kind of lack that a little bit because you're reacting to messages. And messages can be anything. You can pass a null. You can pass a string as a message. You can pass any, like I said, anything. It's very hard for somebody who's just starting to look in Hydra, for instance. There are all these hundreds of messages being passed back and forth. It's like, who receives it? Who is going to react to this message? And if you send a message to an actor that doesn't know what to do with it, you're going to get a dead letter. And dead letters are very hard to debug as well, because sometimes you don't really know. It's hard to track it all the way down to the source. And debugging is also, like I said, the Cryo, the dead letters are tough to debug. And the last thing that I want to bring up, and this is kind of there's a silver lining to it. Akka has a very aggressive release cycle. I don't think they release a new version like every 2 weeks. I'm joking, but it's very fast-paced, which is awesome. But the thing is, if you have different libraries that are all using Akka, you're going to have conflicts, right? So you're going to have, but for the most part, we haven't had a lot of problems, just a couple of times with the remoting again. But for the most part, Akka does a good job to keeping newer releases with older still compatible. But you're going to have like Cryo, for instance, use 2.5.1, right? And we need 2.5.4. So there's some, so you have to, it's just challenging to make sure that if you upgrade Akka, everything else is still going to work. There's no way, you still have to go through that process. So Akka is based on an actor system. So it's really an implementation of an actor system. And really, so what's an actor, right? We can think about an actor as something that encapsulates behavior, reaction. So you send a message to something, it will just reply. It will just do something with that message. That's the behavior. Actors also encapsulate state, like variables that define at what stage in the process the actor is. We don't use a lot of actors with like stateful. We don't like, because it's not as Akka allows us to do that, but it's not as elastic or as scalable as having completely stateless actors. So what we do, a lot of our messages keep the state. So instead of keeping the state on the actors themselves, we send messages that have the state. The entire request, the entire payload, we send that back and forth. Now the downside of that you might want to think about is, now if it's a local actor system, you're good, right? Because it's just within the JVM, you're fine. But if you're sending that across the network, your messages are a little bit bigger now, or a lot bigger, depending on how big your state is. And then in that case, it might make sense to switch over to a stateful actor on both sides, if you're sending like very fat messages, a lot of information in them. And actors have a mailbox, and basically when a message comes in, it gets put into a mailbox. And there's a bunch, you guys can look it up later, there's a few different implementations for Akka. And the idea is that in a mailbox, it goes back to resiliency, that you can pretty much set up your actors so that if they're initializing or if they are in error, you can stash your messages, right? So like say that I have a Kafka producer that's supposed to send messages to Kafka, but Kafka's down. So what the actor will do, it will keep, hey, give them to me, because the order, we keep order. The mailbox in Akka is like a stack. And then we just basically keep stashing those messages while Kafka is down. When Kafka comes back up, we get a notification, then we just basically unstash all those messages, and then they're in Kafka now. So that's the resiliency that I'm talking about. So the application is still running. Kafka is down. Somebody's fixing Kafka, but Hydra is still running. They're still getting messages. And then when Kafka comes back up, we just send everything. And Akka allows us to do that. And if you look about how actors and hierarchies, there's a parent and children underneath that parent. And that's pretty much what I mean here, child actors. So an actor is responsible for supervising its children. When there's an error in the child actor, the parent actor gets notified and can react to it. And can basically say, hey, it's a really bad error. I have to stop that actor. Or no, just resume, just keep going. You know, we're working on it. So it's up to the parent to decide what to do with the child when there's an error at the child level, which is a very powerful concept. There's no try-catches, none of that. And actors at Reactive, so the way to talk to actors outside an actor system is through an actor ref. It's basically, an actor ref is an object that can be passed freely around your application. And the idea is that it's an interface that we talked about, right, between the internal implementation of your actor and the external system. So there's no, it's very isolated because there's no leaks. We look at an actor ref, there's like 2 or 3 methods that you can call. So there's no implementation details that will ever leak from an actor. And the other one is like the location. Like, because now you have location transparency, because an actor has a location, has a path associated with it. But you, as a producer of messages, you're basically talking to an actor ref. If the actor is local, or if it's remote in a cluster, doesn't matter, you don't care, because you're only sending messages to the actor ref. So it's a powerful concept when it comes to elasticity and location transparency. And then Akka has 2 ways, actor refs and actor paths. So actor ref we talked about is the actual live instance of an actor. And an actor path is a logical destination and address of an actor. The difference is that actor paths are easier to pass around, but the difference is that an actor path may not be valid. An actor ref, you know that it's valid, right? There's an actor residing there, but an actor path may just a string, may be something that doesn't really exist. And that's kind of what they look like. This is an actor path. So the protocol in the beginning, and then the address. The first one on the top, that's a remote actor. So you have like Hydra at localhost, that's the address of the actor system, and the port where the Akka TCP protocol is running. And then the path. And then the one on the bottom is a local actor. And these are paths, right? And the assumption here is that when I send a message to this actor, there should be an actor on that path. If there isn't, I'll get a dead letter message on the source system. So it's one of those things. Yeah, it's like when to use actor ref and actor path, something to think about. All right, so deploying remote actors, like we talked about, you basically, this is it, and that's what I was talking about, the power behind Akka, right? Because you can basically, using the configuration file, you can change the entire behavior of your actor system. So the provider here, there's local, cluster, and remote. Those are the different types of actor systems that we can run. This one here is a remote actor system, meaning that all actors are remote by default. So you incur, even though you may be running those actors within the same JVM, you will still incur serialization costs, just like Spark. Spark does the same thing. So even if you could be running Spark on local mode, but you're going through the same serialization protocol. And that's a good thing because the idea is if this is actually a remote actor, you would be able to see if it works or not, like on your tests, right? And here, basically what that means is that whenever Akka tries to instantiate an actor with that name, it's going to do so in that node, in that host. So you could be calling that a new actor ref from any node in the cluster, but it's configured, the Web Analytics Ingester actor will only reside on that node. So that's kind of how we control scaling at the actor ref level. And actor is elastic, we talked about it, and the example is just basically this. So actor has this idea of a router. So you could send messages to a single actor or to a router. And that router can just route messages. There's different routing implementations as well within Akka. And the idea here that we see, we're using the round robin, and this is all stuff that's actually like from the platform. There's actual examples. So this is all stuff that we have done. And the idea is that it's a round robin pool that shrinks and grows as well depending on the utilization of the actor system. And Akka handles all the stuff behind the scenes for us. And it's all matching by name. So whenever there is a an actor under that path, service manager / Kafka producer, it's going to use that router. So it's like, this is like a connection pool, very similar to connection pooling, but at the actor level. Then last thing about Akka, just sending messages. There's two ways to send messages. I don't know if you've seen like the exclamation point, like the bang operator, and the ask. The exclamation point is like fire and forget. Send the messages synchronously and go. Just go, keep going. And the ask returns a future, a Scala future. So we're very, very, very extremely biased towards tell. So this is tell. Tell is the exclamation point. The other one's called ask. If you're trying to do anything on the platform using an ask operator, you're going to be asked why. And you better have a very good example, I mean a very strong use case as to why you use an ask and not a tell. Because even though it's not a blocking operation, it's still a future. It's going to run on a separate thread, but there is a cost associated with setting up the future. There's a promise in Scala that you have to set up. There's a future itself that you have to monitor now. There's entire functional, the monads, the on-complete that Akka is going to have to kind of built into your call. And the idea is if you design your system well, for the most part, at some point you may have to use ask, mostly at the endpoint layer, all the way down the stack. Is that you don't need to do the ask, because if you do a tell, the messages go with the sender reference. So you can always reply back to the sender with the reply later, and the sender can react to it. So that's the idea. The idea, and this is the difference, right, from procedural programming, is that you have like object dot do this, and you're waiting for the do this to come back, as opposed to Akka, hey, actor, go and do this. Let me know when you're done. You know, just do something when you're done, right? I mean, I'll wait. I'm not going to wait, but I'll react to it when I get the answer back from you. And these are the constructs that we're using mostly around like Hydra Ingest. So Hydra Ingest is that area of the platform where the idea is to ingest data as quickly and as fast as possible. And the idea behind, I mean, what's the value added, right? So we have the abstraction layer on top of everything. And the idea is that we're trying to mitigate message loss. We'll talk about that. And data format is secondary in the sense that we'll take JSON payloads, we take streaming payloads, we'll take files, we'll take anything that you want to send us. The idea is that the messages that are coming in should somehow describe themselves. That's the only catch to use the ingest endpoint. You can send it anything, but describe what you're trying to send somehow, and we'll see what that means. And also the idea behind the Hydra Ingest endpoints is to provide automated replication, and we'll see what that means. But the idea is that a message can come in and can be replicated to Kafka. At a bare minimum, everything goes to Kafka, but we can also publish that same message to a RabbitMQ exchange, for instance, at the same time. We can fin it out. And we talked a lot about this, like when do we enforce metadata for ingestion? And it was a very contentious discussion at times, but we decided that we should capture metadata at ingestion time. And that basically means that what I was talking about, that if somebody's sending a message to Hydra Ingest, they will have to provide some type of metadata to describe what they're sending. And why do we do that? Because we're trying to automate a lot of this, right? We're trying to automate data pipelines. We're trying to have some very basic constructs around data quality. And remember, like back in like the first couple of slides about data discovery, if we have a metadata layer here, we are half the way there, because now the streams describe themselves. There's documentation about every Kafka in Kafka, every topic in Kafka, sorry, embedded within the streams themselves, because the schema is part of the stream. That is a very powerful concept, especially if you're trying to materialize data from Kafka into a Postgres table. We do it now. We don't even have to write DDLs, because we extract the DDL from the schema itself, and we translate a never schema to a database DDL create table statement, because we know the fields that are required, know their names, their types. So there's a lot of value in that. So because of that, metadata is a first-class citizen in the platform. And we picked Avro, right? And why Avro? So Avro's been around for a while. If you worked with Hadoop before, chances are you've seen Avro. And Avro has, especially for a continuously running streams of data, it's appealing because it supports evolutions of schema. So you can evolve your schema. Add fields, remove fields, change the name. There is no specific format. You can have development teams still producing JSON. We'll do the conversion behind the scenes, just JSON. It's called a generic record in Avro. There's a lot of community support. Confluent, that's one of the major proponents of Avro. And there's other companies, like Uber uses Avro too for their metadata layer. So Avro is becoming like the de facto standard for sharing metadata between the components of a data platform. There's Avro to Parquet converters, Avro to Postgres, so Avro is powerful in that sense. So everything in Hydra happens with an ingestion protocol, and this is what I was talking about, the request. So you have the raw payload, and that can be anything really. So this is a message that's going to go into Kafka. And that's the metadata that I was talking about. There's like 3 pieces of headers. If you use the HTTP endpoint, there's like 3 headers that you add to the request itself. The Kafka topic, where do you want it to go? The validation, that goes back to how we want because Avro provides data quality constraints, so we can actually validate some of these messages as they're coming in, or like required fields, all that kind of stuff. And the Avro schema that we're using. So when we put those 2 together, that becomes the Hydra request. And that gets published to all these ingesters. So Kafka is just an ingester. And basically what the Kafka ingester does is it's listening for requests with that specific piece of metadata attached to it, a Kafka topic name. And if it has that, it will join that replication protocol. So the idea is that every ingester is looking or is listening for specific pieces of metadata that will react to. It will react to specific pieces of metadata. And then the last piece is just the actual transport. It can be Kafka, Postgres, and Elasticsearch. And they're very defined. There's the publish phase, the transport phase, the validate phase. And we picked different phases basically because of that, right? We try and kind of go back to reactive principles, divide and conquer. We want to make sure that the actual tasks are all asynchronous and they're small. So if there's an error in the validation protocol phase or in the publish protocol phase, I can react to that only. And I know exactly what to do with that piece only. And they're small, asynchronous tasks, and we can isolate them a lot better than if it's just like a massive actor that does everything. And this is just a little bit of Scala code. So this is what the ingester looks like. It's a trait. It can be mixed into any Scala class or a Java class. And this is the protocol, the publish phase, the validate phase, and then the acknowledgement messages from the transports, record produced and record not produced. And this is what the Kafka ingester looks like. And basically if you look on publish, it either sends a join message or ignore message based if the Kafka topic is present in the request. And that's if it sends back a join message to the supervisor, that's kind of how it's going to be included in that replication protocol for that message. And this is kind of a newer thing for us. We added some delivery guarantees. And what we're doing, we were also using Akka for this. Basically, the idea is that Akka has at least one semantics. And what happens with that, the way that we do it, when a message comes into a Kafka producer, if it gets tagged with that metadata, like a delivery strategy of at least once, then this whole machinery goes into play. And the idea is that we save that message to a local journal using RocksDB, which is also provided as a plugin, an Akka plugin. We send the message to Kafka, and then Kafka has an asynchronous callback. It will call back the producer saying, hey, I got the message, and I produced, this is the offset, this is the node, this is the leader. And then if we get the message back, we delete that from the journal. If we get an error, then we don't, and then we just basically keep trying over and over again. And then Kafka is our storage layer behind the scenes. And really quick, if you guys haven't seen or heard about Kafka before, you can think about a messaging system that's based on distributed logging semantics. And so it's scalable, it's fault tolerant, it's very stateful, there's strong ordering within the same partition, and it has very high concurrency levels, both on the producing side and on the client side. And just like Hydra, Kafka also has a replication protocol. You send a message to a topic has a specific leader. So a message cannot go to different nodes. There's only one leader per message, and the message gets replicated to whatever replication factor for that topic is. And if you think about replication is really about resiliency, right? I mean, that's kind of how Kafka tackles that third box in the reactive paradigms that we talked about. It's replicating the data as much as you wanted to, and the cool thing about Kafka is that behind, there's all this complexity, partitions and in-sync replicas of data, but from a consumer perspective, even a producer perspective too, it really looks like a globally ordered queue, even though you have different partitions on the back end. So it's a powerful concept that you're able to basically use Kafka at a very high level if you want to. And behind the scenes, this is what's important for us. We don't really care about the messaging properties of Kafka. We care about the log. We care about the distributed log. So it's a linear structure, like this, and messages get added to the end. And the cool thing about Kafka that makes it different from Rabbit or any messaging system is that consumers have a position. The fact that a consumer consumed a message from the log does not mean that the message gets deleted or gets thrown away. Messages can be replayed. If I am a consumer, I can basically control my offset in that stream. So I can replay that stream over and over and over again. And the idea, if we do that, then you have a distributed replication protocol that can be used for many different things, including things like bootstrapping microservices, which some of the things that we're using the platform for now, we're trying to leverage some of that using Kafka Streams. We'll talk about that a little bit. But you could have a compacted, this is how we're trying to do it, have a compacted Kafka topic, and then have a Kafka Stream jobs that's just basically replicating that topic in real time to any bounded context that subscribes to that topic. And then on the other side, we have Hydra Streams. And then really quick, string processing, if you haven't heard about it before, stream is the idea of continuously moving. And there's a little bit of a speed component to it as well. But the idea is that you have this continuously data sets that are always being updated. And in terms of features, it's very similar to a database. You have aggregates, you have filters, group bys, where clauses. The idea is that usually with the streaming paradigm, you have a time component to things. So you're aggregating things over the last 2 seconds, or aggregating things over there's a period of time. And this is what I was talking about, like the federation layer that we're trying to make Hydra Streams more of a federation layer, because there's different streaming platforms, and these are just 4 of them. These are the most prominent ones now. But you have Kafka. Kafka has a streams module, called Kafka Streams. Akka has streams as well that works. Akka has a Kafka streaming plugin or extension to Akka Streams. Apache, Spark streaming, and Apache Flink. So there's all this different, and they're not mutually exclusive, right? But they all have areas where they work the best, right? And we'll talk about 2 of them today. So we're using these 2. We're using Spark streaming and Spark Core and Kafka Streams. So why did we choose Spark? So Spark was the first implementation in the platform. We started with Spark. And we stayed with Spark only for a long time, for like a year. And why did we choose Spark to begin with? I mean, Spark is a workhorse. It's kind of like Hadoop, like on steroids almost, because it's a lot faster. But the idea is that Spark can handle simple data replication protocols from Kafka to Postgres. It can do machine learning. It can do graph analysis. And just throw things at it, and it will do it. So there's a lot of flexibility using Spark. And the amount of libraries available in the Spark ecosystem now is just amazing. If you want to export a Spark data set into Elasticsearch, you can. Into Cassandra, you can. Into Avro, you can. And S3, so it's a very rich ecosystem. And there's also, since it runs on a managed system, or Yarn, for instance, there's restartability. You can control, right? There's a UI that you can go to, see if your job is running. The Spark UI, for instance. So there's a lot that we get from just using Spark. Now, the downside is that Spark is not a true streaming platform in the sense that it works like in micro batches. Right? So, and from what we have seen, from the kind of stuff that we do, getting messages from Kafka, deserializing them using Avro, and pushing them back to the consumer, we're talking about like a 5 to 10 second realistic stream, micro batch time. But that was okay for us, for our use cases. If it's going to take 5 seconds for each stream to run, that's okay. We don't need this to be milliseconds. We're not running a credit card authorization service. If it takes 5 seconds, it's okay. So this is kind of what it looks like on Spark, right? So we have on this side, and this is Hydra, mostly Hydra on this side here. You have Hydra Ingest writing to Kafka. You can think about Kafka as a log, really. That's all for us. That's what Kafka is. And then on the other side, we have Spark replicating the same log to Hadoop, to HDFS. So now, if you remember that slide that I had before, that Hadoop was right in the center. Now Hadoop is just a leaf, right? It's just a node of the platform. It's just a way, it's just a destination for the data that's in Kafka. Other ETL jobs that run on Kafka directly, other microservices, and other transformations in general. And the cool thing about this is that data doesn't diverge anymore. There's only one immutable set of the data, and that's in Kafka. Everybody just gets upgrades from Kafka directly. So the whole thing is immutable. Once the data is in Kafka, it's immutable. We cannot change it. So one of the problems that we had before, microservices was data divergence, right? Because over time, data will diverge, especially because services change their contracts, they add fields, they remove fields all the time. So you need something, and Kafka provides a lot of that layer. So, and why Kafka Streams? Are using Kafka Streams for mostly data replication between bounded contexts. Because, so what's cool about Kafka Streams is that it's an application, right? And if you're a bounded context, you really care about your autonomy. So there's some pushback. I don't want to run things on Spark, on a shared Spark cluster, and I'm not doing that. And the idea behind Kafka Streams is that we can provide any team with a jar file. Here's your Kafka Streams job. Run it within your application environment, and we'll materialize the data behind it. It's almost like having them give them a driver, database driver. So Kafka Streams is really good for that. So medium data volumes, which is okay for us, for what we're doing now for bounded context. We're not talking about millions of records of data. And the downside is that it's very Kafka specific. It's to Kafka and from Kafka. Actually, having Kafka streams materialize data to databases was a little bit of a challenge because it doesn't have the concept of a transaction like Spark. Spark is easy because it's micro batches. Then you can basically start the transaction at the beginning of the batch and commit the transaction at the end of the batch. With Kafka Streams, there's no concept of a batch. It's a true streaming platform. And with that, we had to go around that and basically come up with our own commit transaction mechanism behind the scenes. And it's for basic tasks, right? We're not going to do machine learning or anything like that using Kafka Streams. It's perfect for bootstrapping bounded context. And this is how it works, like for microservices. So very similar. But the difference is that instead of having Spark on that box doing the materialization, it's Kafka Streams. And that runs within the microservice environment itself. And then the last piece of the puzzle, it's called Hydra Spark, and that's basically our abstraction on top of Spark. And the idea is that if anybody is not familiar with Spark, they don't want to write Scala code or PySpark, they can express jobs using a DSL that right now looks like JSON. It's actually a type-safe config file, so it can be HOCON or JSON. And it's really for data flow. So let me see if I can get an example just so you guys can see here. Hold on, give me 1 second. So this is what it looks like. This is a DSL. So you have the source is Kafka, and then your operations, we can filter by value, a database absurd, which is like a data replication to a Postgres table. And this gets materialized as a Spark job. It's a Spark streaming job in this case because you have this streaming interval set here at the top. And then that's it. I mean, all these, Hydra Streams is a newer project. We're still working actively on that. But all these other stuff that I talked about, Hydra and Hydra Spark, they're open source. They're under the Pluralsight organization. So feel free to go ahead, check it out, see what you think. And you can see most of the stuff that I talked about, it's all there. And that's the idea, to keep open source as much of this as we can. And that's it. I mean, we're hiring as well to work on the data platform. So if anybody is interested, come talk to me after. And that's it. That's all I have. Thank you. So I guess if anybody has questions, I'm supposed to tell you to step up to the microphone and do it there.
This is interesting and awesome, but what was the business use case for you guys?
Yeah,
I might have missed it.
No, we did not. That's a great question. So it all started with video services. Video services, Pluralsight was the kind of the catalyst behind this. We wanted to start capturing video metrics in real time, like delays, or what are people doing with their videos? Are they pausing? Are they scrubbing? What are they doing to get more of the user experience, be able to switch from one CDN to another in real time? That was the catalyst. It grew a lot more than just that, but that was the use case that we kind of latched on to. Like, we're going to do this to solve that problem, because that was pretty big for an online content delivery company.
And so just to follow up, how widely is this now used at Pluralsight? Do you use it for other things other than the
Yeah.
video? Yeah.
Yeah, so we're still working towards getting that as ingrained as possible. This is supposed to be the de facto data source of truth for Pluralsight, but right now it's used across all the data teams: data science, data engineering, data analytics. There are some data engineering teams that are using it. I mean, some software engineering teams are using it as well. And we also use it to capture product data, like browser data, like clicking and things like that. So it's used anywhere where there's data being consumed. We also replicate data from internal services, from Rabbit Exchange, Rabbit MQ. We replicate data from Rabbit into this thing because it's easier to report on that later. So it's being used across the entire organization, and it's growing, right? I mean, we're trying to get more and more people contributing data to it.
Cool. Okay, thank you.
Hey, that was a great talk. Whoa, I'm loud here. So that was a great talk. So I was a little confused on the front part where you said you prefer bang versus question mark, where you said async versus the future. So I'm assuming that you have use cases that are extremely business sensitive and you don't want any data loss. So what happens in that scenario where it's an async and your Akka ingester goes down?
That's a very good question, right? I mean, and there's different ways to talk about that. And I can try to summarize it as much as I can in a minute, or we can talk more later, okay? But the idea is that at some point, just like a future in Scala, right? I mean, you can keep passing that future around for as long as you want to, but at some point, you're going to have to complete it. You're going to have to do a non-complete and react to it. And the idea, that from what we have seen, is that we keep that layer all the way up to the endpoints. In our endpoints, if you go to the code base, you'll see some endpoint operations are ask operations. And the endpoints in Akka have a timeout attached to them. So there's two things that we do. We try to keep the ask. There's different ways to do it, right? But we try to keep the ask up the stack as possible. That's one. Number two is that for each request, and that's what we do with ingest. Each request, it's all asynchronous. There's no ask on ingest. But what we do, we have an actor for each request, and that actor gets a copy of the request context, the Akka HTTP request context. So when you hear back from the ingester, if it's completed, then you complete the context. Exactly. So we can keep it fully asynchronous like that.
So you also mentioned that there was a RocksDB journal that you're keeping. Is that the mechanism that you're using to guarantee? Okay, got it. So, but if any of that aspect, and that RocksDB is in memory.
The RocksDB?
That RocksDB?
No, the RocksDB is on the file system.
Oh, sorry, that's on the file system, but the access to that RocksDB map is in your original producer.
Yes, in the producer, yes.
Got
Each producer has its own copy.
So then that's how you'll notify if there was an error.
Right.
That's great, thank you.
Any other questions?
What features from Akka would you discourage people to use after?
Discourage?
Yeah.
That's a good question. Remoting. Think about it if you really need it. Remoting for sure, yeah.
What about?
And I would, so remoting, and honestly, like the journaling thing that I was talking about, it's new. It's on production now, but it hasn't been in production that long. And it's a newer feature in Akka 2.5 as well. So I'd be cautious about that one. I don't know. See, what I'm concerned about that for me specifically is that if we start having a lot of people producing messages with that type of delivery strategy, if that may become a file system bottleneck. Because now we're writing all these messages to a file system that's not really meant to be as distributed as Kafka, right? So that is an area that there's a little question mark for us there as well as to how feasible is to keep this as an alternative. So right now, that's not the default. The default is at most once delivery, using Akka resiliency, memory, mailboxes, and somebody, if it's a very critical piece of data, like a revenue transaction, that you want to make sure that gets delivered, then we tell them, hey, yeah, tag this message with this delivery strategy, and then we'll keep it. We'll keep it at least locally in the journal until we get the, so that's an area that so remoting for sure, and then the at least once delivery, just because it's kind of new. Even the documentation on the Akka website, it's still kind of, it's hard to understand, so it's more of a different, and remoting, they're also doing something with Avro now, which is better, but I've seen errors that if the actor system takes too long to reply, it shuts down, which is not something that you want to happen in your production environment. That thing shut down, I mean, it's not going to be good. But we run this on an elastic load balancer from Amazon. It's all AWS, should have said that. It's all AWS services. And there's a load balancer in front of it. But, you know, does that answer your question? I mean, Akka is pretty stable. We love working with Akka, but remoting for us has been kind of a pain point, to the point that I don't know if it even makes sense to use it anymore. And the journaling, it's still, because remains to be seen how journaling is going to behave under heavy load on production. And
you include clustering when you talk about remoting?
Yeah, we've done. So the Hydra Streams, it's an Akka cluster. That's how we run Spark jobs on Hydra Streams. Every Spark job DSL that comes in gets instantiated within a node in the Akka cluster. Again, it's one of those, right? I mean, the more moving pieces that you add to the equation, the more complex your system becomes. And that has been a challenge for us on that side, on the streaming side, how to deal with errors properly on an Akka cluster, how to surface those errors back to the user. There's a lot of feedback that we've been getting from our users that the streaming jobs that we run now, they don't really know what's going on with them. They could go to the Spark UI, but we want to have something that's easier. It's almost like fire and hope for the best. We're trying to work, how can we make those metrics in Spark more visible? So we're sending those to like Graphite now and seeing if there's anything we can do to increase the confidence level of users using the streaming side of the platform. That is an area that's in active development right now. The ingestion side is pretty good, but streaming is a lot more challenging to get to that same level of visibility and confidence. You know, because when you get to the streaming, there's also so many things could have gone wrong by then. Right? I mean, data may not have been ingested. Data may have been invalid according to the Avro schema, but from a consumer perspective, they don't really know what happened, you know? So that's one of the areas that we're working on as well, how to tie those two together a little bit better.
And one more question. So when you brought the system to production, how hard was it to tune it, to configure it specifically for your needs? What were like the default configurations, for example, that were completely aberrant, or that you had to? Can
you repeat that question?
Yeah. How much effort did you guys have to do to configure all those Akka configurations for your system to be actually?
That's a good question. So Akka uses type safe config. So we have all the defaults are provided by the application itself within the application with the jar file. And what we do we have a DevOps team, a Pluralsight, and what we do, we basically use an external file to override the default if we need to. So configuration hasn't been too much of a pain because of that, because we provide sensible defaults for everything. And then so it's whatever's within the jar, and then there's a file under etc, it's under etc Hydra, and then application.conf. That can also be overridden with any environment variables that the ops team set for the node that's been. But the feedback that I got from ops is that it's a very configuration heavy project. And that's expected because you have to configure the bootstrap servers in Kafka, all the Kafka properties, the X, the serialization, the formats, and same thing for Spark, same thing for, so there's a lot of configuration, more than what we're used to. But it's just because it's an integrative, it's a platform using a lot of different tools.
Hey, on the last point on the DSL that you have for Hydra Spark.
Yeah.
Okay, how do you convert that into running Spark at runtime?
Yeah, so when you submit, what happens, we basically parse that DSL and check to see if it has a streaming component to it or not, and then we match that names. Those names that you saw, database absurd, they actually match to a class. They match to a class called database absurd. So it's all dynamic using reflection at runtime.